Hi Pre-Calc gang, time for another online lesson, 3.5, Continuity and End Behavior. I should mention that these are really heavy-duty calculus terms, especially the notion of continuity, and so we're giving you a little foreshadowing of what that's all about here in this lesson, help you in that transition to calculus when you take that. First of all, I want to talk about continuity in a continuous function. And you've seen plenty of continuous functions. The key thing here is a smooth curve. Sometimes we talk about the pencil test, that if you were to run your pencil or pen over the function there, you would not have to lift it off the paper. So a nice smooth curve, no breaks at all. This is a graph of the sine function, which we'll be studying a lot when we delve into trigonometry later this quarter. But as you can see, it's a nice smooth curve here, no breaks or anything like that. There it goes. Now a continuity test, this is not huge, but it is when we get to calculus, so I'll mention it. Good to write this down. We say a function is continuous at x equals c. The c would be a particular x value. So it has to be defined there. F of c exists. Number 2, the function approaches the same y value on the left and right sides of x equals c. So for instance, if we look at our sine function here at 1 or 2, 1 let's say, as it approaches from the left and from the right, the y values are the same. And number 3, the y value of the function approaches from each side is the same as the actual definition up here. So that's the continuity test. Again, we won't worry about that too much because continuity is pretty Alright, now we will spend more time with this. These are the types of discontinuities. So really good if you need to pause and copy down this chart. Really 3 types of discontinuities, and again, if continuous function is a nice smooth curve, discontinuities then mean that there is some break in the graph. So here's our 3 kinds, and I've graphed 3 functions to give you some examples of that. First one is called an infinite discontinuity. Anytime there's an infinite discontinuity, you'll see some of these vertical asymptotes. We represent those with dashed lines when we draw them on paper. On your graphing calculator you won't see them, but you'll know you have vertical asymptotes when the graph shoots way up or way down around a certain value. This is the graph of y equals 1 over x, and clearly x is not defined. You can never have x be 0 in this case. That's why the graph shoots way up and way down there. So this is a classic case of an infinite discontinuity. Second example here, jump discontinuity. Here are one of these piecewise functions that we studied about in an earlier chapter. And I've graphed this on the graphing calculator. When x is less than 0, we have a certain thing graphed. When x is greater than or equal to 0, we have another portion graphed. Clearly at 0, there's a big break. You could not trace your pencil without picking your pencil up to continue this function. And so the break we call a jump discontinuity. So you can usually tell at the same x value there's going to be a different y value, thus the break in the graph. So that's jump. And the last one is point discontinuity. Now when you look at this particular function, it looks perfectly normal. It looks like a straight line. However, by looking at this denominator, you see there is one value that would make this denominator go bad. In other words, would make it equal to 0, and that's at x equals 2. So if you were to look at the table of this particular function, you would see that sure enough there would really be a little hole there at x equals 2. And so it's probably more appropriate to graph this by putting a little open circle here right at 2 to show you that there is indeed a break in that graph. So we call that a break or a hole a lot of times. So make sure to take some time and copy this chart down. We'll be referring to this quite a bit. Let's just do an example, and we'll look at continuity. It's possible for a function to be continuous at a point and then not continuous at a point, and really the same function. So for instance, let's look at this function here, y equals x minus 5 over x plus 3. Right away you should become a little suspicious whenever you see something in the denominator, because if we can ever make that denominator to be 0 with a particular x value, then we're going to have a discontinuity right there. So for instance, first of all, part A here at x equals -3, sure enough, here's our trouble spot here. If you put -3 in place of x, that would make that denominator equal to 0. And we can tell that if we look at the table then of this function, that at -3 there is an error. So clearly this is not continuous, and if we were to label what kind of discontinuity it would be, well, once again we have that huge break in the graph. We do have one of those vertical asymptotes here that you can see. The graph shoots way up and way down, and so that makes this an infinite discontinuity. When we do this function biography later in this unit, you'll be have to do some things with that perhaps. Alright, let's look at x equals 1. Now at x equals 1, it looks like it's kind of a nice smooth curve right around there, and certainly we can see from the table that it is defined when x equals 1, y equals -1, so it is defined there to be sure. So actually at x equals 1, this is continuous. So a function can be continuous at a certain point and not continuous at a certain point. However, if we want to classify this function overall, we would have to say that it is discontinuous because of that infinite discontinuity. Alright, another key idea here really, and the last one is in this lesson, is something called end behavior. End behavior. And what that means, didn't really mean to write over that, sorry. What end behavior is what happens on the ends of the graph. What the y values do as this absolute value of x becomes greater and greater. And so when you see the absolute value of x, well, that means as x gets really large and also as x gets really small. Anytime we do end behavior, we will always write it like this. There's always two parts. We say as x approaches infinity, that's the right end here, what happens to the y values. And then we have to consider the left end. As x approaches negative infinity, what happens to the y values. Alright, so let's look at a particular example here. So I've graphed this on the graphing calculator. Kind of an ugly looking function, 4x to the 5th plus 2x to the 4th minus 3x minus 1. So we want to describe the end behavior. Remember there's two parts. So we would say first of all as x approaches infinity, and I got to figure out now what about the y values. What are they doing when x gets really, really big? Well, you can see this graph just shoots up higher and higher. You might be able to look at your table for some insight there. But we would also say that y approaches infinity, positive infinity. Those y values are going to keep getting bigger and bigger. And then, don't forget there's a second part. I also have to say as x approaches negative infinity, what happens to my y values? Well, in this case, you can see that as my x values keep getting smaller and smaller, it looks like my y values are also going to keep getting smaller and smaller. And so thus I'm going to say that y will be negative infinity. So that's end behavior. We'll be practicing on some more of these. It's not a terribly tough concept. You can do most of it just by looking at the graph. So that's the deal there. Alright, and this coming week here, you can see there's our royalty, our king and queen from this past week. I have a little trivia question for you. I am looking for, believe it or not, I graduated from Blue Earth in 1979. The first two people that can come and tell me who the king and queen were in my senior year, this would have been 1978 in the fall, I suppose. First two people from each section, I'll give you some extra points on the left side of your assignment card. So that's a little trivia for you, 1978 Blue Earth King and Queen. Alright, thanks guys, and we'll see you in class.